Hello, everybody. So we're going to keep going with differential equations. Last time I tried to give a little bit of a big overview in some of the situations in which we might use it. I expect it felt a little bit maybe overwhelming. Don't worry, we're gonna start to focus down now a bit on what in particular we want to know about differential equations in the next couple of videos. You know, it's a huge topic, so I was trying to give a little bit of a sense of the breadth of it, but I still can't cover, you know, talk about huge regions of it. So let's start focusing in on what kinds of things we're going to start doing with differential equations. So let's first of all give our definition again. So a differential equation. This is just an equation with an unknown function and some of its derivatives. This is a pretty untechnical definition. Some of its derivatives. We'll even stop, sorry, I can't spell and talk at the same time. We'll even find sometimes the function itself might not appear in the equation, just the derivatives of the function, though often it is there. And when we talk about a solution, so a solution to a differential equation is a function that satisfies the equation, right? We'll do some examples here in a second, but it's similar to when you solve an algebraic equation like x plus 2 equals 5. The solution is 3, because 3 is the number that when you put it in makes that statement true. Or if I said x squared is equal to 4, then the solutions are, or the solution is 2 numbers, right? We have more than one possible answer there. 2 and -2 both satisfy that equation. So let's do an example and see exactly what I mean by solution. So we'll do a very straightforward y prime equals 2x, right? So we've got a derivative and in this equation. And so we're looking for an unknown function, y, and here's an example where y doesn't appear in this equation. We want to find a function that satisfies this equation. For instance, here's a function, right? So if y were equal to x squared, or I called it f of x because I'm going to do a couple different solutions, so I want to keep them different, right? So if I'm calling this y, then it's clear y prime is equal to 2x. But we can also do a solution, for instance, of x squared plus 13, right? If I call this y, then we also have the case that y prime is equal to 2x, okay? So notice here that there's more than one solution. In fact, there's a family of solutions. We can write our solution in a very general way as y equals x squared plus c. This sort of captures, this does capture this family of solutions, right? Every parabola with its vertex at x equals 0 has a derivative of 2x, right? The plus c can just raise and lower that function, okay? So that's an example. Notice that both of these equations all satisfy, sorry, these functions satisfy this differential equation, right? Meaning it's true for the function x squared plus c that its derivative is 2x. Let's make it a little more complicated. Let's use the space over here. Let's look at y prime equals -5y, okay? Now, you may have seen how to get the solution in the first example, right? It may have been almost obvious what function has a derivative of 2x. This is a little bit trickier, okay? And we will talk very briefly. We've kind of already shown a method here. I essentially found the antiderivative of both sides of this equation, right? Taking an antiderivative of y prime gave me y, an antiderivative of 2x is x squared plus c. So that's one method for solving them. something like this takes a much more complicated method, which we won't get to until the next video, but we will be able to do this kind of a differential equation. But right now I want to focus on what it means to satisfy it. So a first equation that satisfies this, let's look at the following. Y equals e to the negative 5x, right? So I'm claiming this is a solution. So let's see that it satisfies this equation. If I take the derivative, I get y prime is equal to, well, I have an exponential, so we get the same thing back, but then we get a chain rule. We have to multiply by negative 5. Let's just rearrange things. This is negative 5 times e to the negative 5x. I don't know why I put parentheses, but notice e to the negative 5x is just y, right? That's what the solution is. And so this function does satisfy this differential equation. In fact, so does this one, right? If I take the derivative of y equals 3 e to the negative 5x, I get 3 e to the negative 5x. From the chain rule, I get a negative 5 popping out, but that 3 e to the negative 5x is just y, okay? And so in this case, similar to the other one, we have a general, a more general solution here is if I throw any constant in front of that e to the negative 5x, I'll get something that satisfies this equation. So again, there's a family of functions that satisfies this. Let's do one more. Let's look at y double prime. Let me make that clearer. Y double prime, the second derivative of y, is equal to negative 4 times y. Okay. So here is, I'll just give a solution in this case. This is more interesting, maybe. It's a little bit trickier to think about. We've got a second derivative. So here is a solution. Y equals sine of 2x plus cosine of 2x. So if I have y prime, we'll get 2 cosine of 2x minus 2 sine of 2x, right? Just using the definition of using trig derivatives and the chain rule. And when I take a second derivative, I'll get negative 4 cosine of 2x minus 4. Oops, I forgot to change that to sine when I took the derivative. Negative 4 sine of 2x minus 4 cosine of 2x, which I can factor out the negative 4, and I have sine of 2x plus cosine of 2x, and then of course that is just y, negative 4y. And so that function satisfies this differential equation, right? So what I've just done in all these cases is what people have always been telling you to do in algebra. You find a solution, plug it back into the equation to see if it works. And plugging it into a differential equation means you have to do a little bit of work, right? Eventually, not in this course, we'll get to situations where you might have something like y minus 2y prime equals 3y plus 7 or something like this, right? And you'll learn some methods, let's throw an X on there, to solve this differential equation, and you can check your work by taking the second derivative of your function, taking the first derivative of your function, and seeing and arranging your function in this way to see if it's true, if they're actually equivalent to each other, right? So we're doing that same idea of checking your work. What we've skipped over in these examples is how do we actually find the solution? So we're skipping that part right now. I just want to have the idea of what a solution is. I want to also give a little piece of vocabulary here. So one word you'll hear around differential equations is the order of the differential equation. And this is just the highest order, the order of a differential equation is the highest order derivative that appears in the equation of the unknown function, right? So in these examples, the first two were both first order differential equations because they both had only a first derivative. This last one is a second order differential equation because it has a second derivative. Or that example I wrote down a minute ago was also second order. It had a second derivative and a first derivative and the function, but the highest order derivative was 2, so it's a second order differential equation. Okay, so just a word so we can, you know, there are different methods that can be applied to different ones, so we want to know what kind of thing we're looking at. Okay, let's do one more thing in this video. Let's go back and think about that example we started with. Y prime is equal to 2x. And we found that the most general solution for this was, and in fact, let's write out a little bit of a method of how we could, no, let's just keep the solution as is. Yeah, we can think of this as we are integrating both sides of this equation, right? We're finding the antiderivative on both sides. The antiderivative of y prime is just y. The antiderivative here was x squared plus c, and that's how we found our general solution. Oftentimes in practice, we want a particular solution. So a typical problem might be something like find the solution to y prime equals 2x that passes through 1, -5, right? So now we already have the general solution. All we need to do is find the one that satisfies, that hits this point, so that this point is a coordinate pair, a solution to this equation. So if I put in -5 equals 1 squared plus c, I get -5 equals 1 plus c, or -4 equals c. And so now the solution becomes y equals x squared. Oops, I can't subtract numbers. This is -6, right? So what we've done here, if you remember those graphs I looked at yesterday, right? This general form is a family of functions, right? There are all these parabolas that satisfy this equation. My picture's not perfect, but we get the idea. Pretend those are all perfectly aligned. One of them passes through this point 1, -5. And so this algebra we did here picked out which one of these infinite solutions we were in particular talking about. So we will often talk about the difference between a general solution, right? This is our general solution to this differential equation. And this is a particular solution. And to get a particular solution, we're always going to need, I shouldn't say always, there's probably some case where it's not true, but we're going to generally need some extra information, right? In this case, and a point on the graph. Let's do one more example of that. Very often the point that we're given, so we're going to ask the same question, but this time passing through 0, 7, right? So again, if we were the same differential equation, which one of these passes through the point 0, 7? This one's fairly easy to do. I don't even need to write out the algebra. This one goes through the point 0, 7. So now we've picked a different one from this infinite list as our particular solution, okay? Often this is what we have. This is sometimes called an initial condition. Just the value of the function at 0, right? So initial is, I'm pretty sure this is what I've always assumed. It comes from the fact that often these differential equations, we're looking at something that evolves over time, functions that change over time, right? If you're a scientist studying something, it's one way when you start and some other way later. So the initial just is how was it in the beginning, right? So if you're trying to model some phenomenon, you can look at it and you want to predict how it's going to look later. So you might have some information about how it looks in the beginning, right? This is information about how this thing looks in the beginning, and we can use that plus our differential equation to get information about how it's going to look later, right? Now I can tell you if this was measuring some phenomenon, or modeling some phenomenon, I can give you a value for that phenomenon at any point in the future. If X is my time, I just put in values later on and can tell you what the model predicts at those times. So let's do one more example like this that's a little more, let's say, closer to real world application. So this is an example from physics. We'll use a little bit of physics knowledge here, but I'll try to keep us informed as we go if you don't have a lot of experience there. Suppose we are going to launch an object straight up, with velocity 20 meters per second. Okay. Assume, let's see, air resistance is negligible, meaning it's there, it's small enough that we're not going to worry about it affecting our results. The only forces, or the only force acting on the object is gravity, the force of gravity. Okay, so here on Earth. So let's set this up. We're going to have to pull in some physics facts. So the function we're going to be looking for, oh, I should give us our goal. Let's find a function that gives the velocity of the object after t seconds. Right? Meaning, I want to find a function whose input is time and whose output is the velocity of this object. That's my unknown function. Okay? And so I'm naming it, I'm calling it v for velocity. And what we know is v prime of t, when we take the derivative of velocity, we get the acceleration. Okay? This is a measure of how the velocity is changing, right? Here's where we're going to pull in some physics facts. On Earth, we've determined through experiment that the acceleration an object feels due to gravity, we name it g, is equal to negative 9.8 meters per second squared, right? This is assuming up is positive, down is negative, which makes sense, okay? So what that means is v prime, I'm going to drop the of t for now just to make this easier to write down. Since gravity is the only thing acting on this, the only acceleration it has is this 9.8. I'm going to drop the units as well while we do our computations, right? Well, v is a function of t. Negative 9.8 is a constant. I'm going to integrate both sides with respect to t. when we take the antiderivative of the derivative, I'm just getting back v of t. And over here, I get negative 9.8 t and a constant, right? So just to be clear, both of these integrals really should have a constant of integration. However, we can combine them, right? There's some extra numbers floating around, so I bring them all together on one side. Okay, so that's the general solution to this differential equation, this fairly straightforward differential equation. A derivative whose a function whose derivative is a constant. You can see from what we have here is a linear function, right? Linear functions have derivatives that are constants. Now we're going to use the initial condition, the velocity which we fired it with, right? We shot this thing with a velocity of 20 meters per second. So this is, let's reframe this launch with velocity 20 meters per second is another way of saying v of 0 equals 20. Okay, so v of 0, however, is negative 9.8 times 0 plus c. So v of 0 is just equal to c, which means that c equals 20. And so we get our particular solution, our negative 9.8 t plus 20, right? And that gives us a velocity function for this particular object on Earth, right? Obviously, at some point it hits the ground and then this function no longer applies, but it will give us a reasonable prediction of this object's velocity over the time that it's in the air after being launched, right? Assuming that air resistance is negligible, which we did. So maybe it's a fairly, it's an object that's heavy enough and aerodynamic enough that the error doesn't affect it too much. Okay, so that is some of the basics of differential equations. In the next video, I'm going to, we're going to dive into our first more complicated kind of equation we can solve, right? The only two we really showed a method for here were ones that are just finding an antiderivative. We have a function and some simple form that we know how to find an antiderivative for. And those we can just take an antiderivative. So we're going to take it one level deeper in the next video to get some more methods. Okay, I will see you in the next one. Thanks, everybody.